All right, in this next part, we're still going to keep working with linear equations for a little bit, but we're going to bring in fractions, everybody's favorites. So what I like to do when I have fractions in my equation is I actually like to cancel them out. I personally don't mind fractions, but it's usually much simpler if we just get rid of them early on in the problem, rather than trying to work with them. They tend to be pretty cumbersome in equations. So we can solve linear equations with fractions. You can just solve them with fractions, but usually we like to cancel them out at the beginning of the problem. I will say that if you have parentheses, I still like to clear parentheses first, and then I like to cancel my fractions. That's a personal preference, but you could cancel fractions before that if you like. So what we do is we end up multiplying through by any common denominator. Now we try to use the least common denominator. So your LCD, because the smaller numbers we have, the easier the multiplication is, but technically any common denominator would work. So notice here I have a denominator of 4 and a denominator of 3. So my LCD in this case is going to be 12. And what I'm going to do is I'm going to multiply through by 12. Now, technically, we multiply the left side of the equation and the right side of the equation by 12. That keeps the equation balanced, and it makes sure we don't mess up our solution. It keeps it as an equivalent equation. So you can do that first. I kind of like to skip that step and just kind of jump right into multiplying every part by 12. I think that's a little bit easier, but technically we are multiplying both sides of the equation by 12. So what we're going to do is just anytime you have a different piece, you're going to multiply it by 12. Notice that, since this is kind of one fraction, I don't need to write 12 many times. I'm just going to write it once with that fraction. And then I also have to write it on the right-hand side. So even if I don't have a fraction, everything still has to get multiplied by 12 to keep that equation balanced. Now, you could either multiply first or you could divide first. I like to divide first. I think it's easier. So I'm going to clear out those fractions right now. 12 divided by 4 is 3. And then 12 divided by 3 is 4. If you've done this right, you should have no more denominators left. And then what you do is you multiply through with that multiplier that's left over. All right, my camera's being really bad today. Let's see if we can fix it. So here I'm going to do 3 times x, which is 3x, and 3 times 2, which is 6. For the next group, just be really careful. You have a minus sign there. So that minus sign is getting distributed with that 4. So I'm going to distribute a negative 4 throughout. Negative 4 times x, and then negative 4 times negative 1 is positive. And on the right side, I have 24. Now we should have a regular equation, and we're just going to go back to our regular rules. I'm going to start by combining like terms on the left side. So I see a 3x and a minus 4x. So that's minus x or minus 1x. And then I see a plus 6 and a plus 4, which is 10. At this point, I don't have anything else I can do, so I need to move that 10 over with the 24. I'm going to subtract it on both sides. And I have negative 1x is equal to 14. Now, there's a 1 here, so I'm going to divide out by negative 1 on each side so that I can get that canceling. And I have x equals negative 14 as my solution. Now, I'm going to do one more check here, and then I'll take a break for the check on the next one. But what you have to do is you still have to go back to the original problem. So sometimes the checks are actually the hardest part of these fraction problems. And you're going to plug in your answer. So every time I see x, I'm going to replace it with negative 14. So negative 14 plus 2 is negative 12. Negative 14 minus 1 is negative 15. Negative 12 divided by 4 is negative 3. Negative 15 divided by 3 is negative 5. Watch out for that extra minus sign here. So these two negatives are going to cancel. It's -3 plus 5, which is 2, right? 2 equals 2. So it does check out. Sometimes with your checks, you may have to simplify fractions and things too. So they can get a little bit cumbersome if you're going to go ahead and do that check. All right, let's do another example here. So this time, my denominator is a little bit more complicated. So let's see, I have a 4, a 14, and a 7. So I need to think about my LCD maybe a little bit more here. And for me, I'm thinking 28 is probably going to be my best option. That 4 is kind of throwing me off a little bit because I can't just use 14, right? 14 divided by 4 doesn't work. So 28 is going to be, I think, my best option here. So I'm going to multiply everything through by 28. All right, 28 divided by 4 is 7. 28 divided by 14 is 2. And 28 divided by 7 is going to be 4. So any factors I have left over, I am going to multiply. So here I'm going to have a 7x minus 21. Now here I just have a 2 and a 5, so I'm just going to do 2 times 5, which is 10. And then again, just be careful, there's a minus sign there. So I'm actually going to distribute a -4. So I have, let's see, minus 4x minus 20. And again, if you find it helpful to kind of put in that vertical line down the equal sign, just to keep yourself organized, go ahead and do that. So do anything that you need to do to stay organized. I don't have anything to do on the left side, but on the right-hand side, I do see a 10 and a minus 20. So that's going to combine to get -10. And I bring down that -4x. Now I'm going to start moving things around. So I can bring my 4x to the left. 7, let's see, I get 11x minus 21 equals -10. And then I'm bringing that 21 to the other side. I guess we'll stick with purple. And I have 11x equals, let's see, -10 plus 21 is positive 11. All right. Final step is to cancel out anything left over with the variable. Divide both sides by 11, and I have my final result of x equals 1. So I'm going to let you guys do the check for this one at home, but it does check out, and 1 would be your solution here. You do have to do some fraction work. So when you check this one, you're going to have to go and use that common denominator of 28 again to make sure it checks out, but it does check out. Now, your fractions lead into something called rational equations, and we're going to be doing a lot more with rationals throughout the semester, so we're just kind of introduce it today. But a rational equation is an equation containing one or more rational expressions. Now, think of that word rational. Rational means ratio, so you have some sort of fraction in your equation. Okay, so if you see rational expression, you really want to think really a fraction there. Now, these may or may not include variables in the denominator. So our last two examples are actually examples of rational equations that have constants for the denominator, right? So just plain fractions. So sometimes we call those linear, sometimes we call those rational. They kind of fall into both groups when our denominators are just numbers, if they're just regular fractions. However, rationals can get more complicated. So a lot of times what we see with rational expressions as we get into harder problems is that we now have variables in the denominator. So we follow the same basic procedure we did above, but it's a little bit harder because our common denominators now become polynomials, not just numbers. And we also have to watch out for our domain. Now, domain refers to our x values that we can plug in. So we have to remember that we cannot divide by 0. This is a really big thing we have to watch out for, right? We cannot divide by 0. Divide by 0 is undefined. So we do have to make sure we exclude these values as we're solving. A lot of times when we're solving rationals, we get what are called extraneous solutions. And this definition is not in your text, but it's an important one, so I want to put it in here. Extraneous solutions are values that appear when you're solving an equation that look like they're solutions. So you get the answer at the end, but when you go to check them, they don't actually work. So they're not real solutions. And this can happen one way with getting a value that makes the denominator 0. They can also happen with other values too. So your book kind of glosses over that idea, but particularly for harder rationals or just more involved rationals, it's not just denominators being 0, but other extraneous solutions can come out. So we really like to check our answers when we have rationals. I highly encourage you to do that because sometimes we do have issues with those rationals. And they basically arise because we're multiplying by variables and by polynomials. So we can generate extra solutions by accident that don't actually work. That's really what's happening. So let's solve a couple examples here. So for my first problem, this is a rational. It's not just linear. And that's because I have variables now in my denominator. So if I didn't have variables, I just had the 1/5, then it's rational and it's linear, kind of falls into both categories. But once you bring in those variables in the denominator, it's rational. It's a little bit more to watch out for. So for my LCD, what you just need to do is to combine all the denominators together. So I usually just kind of go through the line and make sure I'm not missing anything. So for my first denominator, I have an x. So that's going to be part of my LCD. I'm just going to put it in parentheses as a factor. My second denominator is a 5. I don't have a 5 yet, so I'm going to bring in a 5. Now my last denominator is a 2x. I already have an x, right? I already have the x listed, but I don't have the 2 listed. And 2 is not a factor of 5, so it's not there. So I'm going to bring in that 2 as well. So my LCD is going to be 10x. 5 times 2 is 10, and then with the x. So that's how I like to do it. I'll just go fraction by fraction and making sure that all those factors are accounted for, okay? I don't need another x, I already have one. If this was an x squared, that's different. Then I need to have 2 x's in my LCD because I have a square there, so that's different. But if I already have 1 x and that's all I need, then I'm done. So I'm going to multiply everything by 10x. And now I'm going to start simplifying. So in the first thing, I can cancel an x and an x. And then what I have left is a 10, and I have that 1. So 10 times 1 is just 10. Now in the next group, I can't cancel any x's, but 10 divided by 5 is 2. So I have a 2x left here, and then a 1. So 2x times 1 is just 2x. And then in the last group here, the x can cancel. And then 10 divided by 2 is 5. So I just have a 5 here. Let me use a different color here. So for this one, you have the 2 and the x that's getting distributed there. Here I just have a 5. 5 times 3 is 15. So once we cancel that denominator, we actually have a relatively easy problem now. So the hard stuff is up here. So now I'm going to bring that 15 to the other side. My x's are already on the right, so I'm going to leave that 2x alone and move my 15 instead. And I'm going to get -5 equals 2x. And I can divide both sides by 2. And I have x equals -5/2 for my answer. Now, we're not quite done yet. We do need to check this. So one thing you have to watch out for, just kind of a side note, watch your denominator. So if I look at my original denominators, I have an x here, and that value cannot be 0. So I need to make sure that x is not 0. Now my next fraction, my denominator is 5. Technically, I need to make sure that 5 is not 0, but that's not going to happen, right? 5 is never 0, so I don't have to worry about that one. And then for the last one, I need to make sure that 2x is not 0, but that would only happen if I solve this when x is not 0. So I don't need that one as well because I already have it. So the big thing I need to watch out for here is making sure my answer is not 0, because that would make the denominator 0 as well. And my answer here is definitely not 0. So I am good. I don't have anything to throw out initially speaking. Now, I still recommend you do a check. Like I said, for right now, I don't think you're going to see this too much, but you could still generate extraneous solutions that are something different beyond just the denominator issue. So I'm going to go through the check here as well. And it's a good practice with our fractions anyway. So I'm going to go back, and anytime I see an x, I'm going to plug in my answer of negative 5s. And I'm going to simplify. So for this first part here, when you have 1 over negative 5/2, that's the same thing as saying 1 divided by negative 5/2, right? This is kind of a big division bar. Remember, when you're multiplying with fractions, what we are dividing with fractions, excuse me, we change to multiplication and we flip our second fraction. We take the reciprocal here. So this whole thing is actually just 1 times negative 2/5. So I can simplify that first piece to negative 2/5. Oh, sorry, this should be an equal sign here. Here I have 1/5. And now in the next group, it's actually not that bad. My denominator, the 2's are going to cancel, right? 2 over 2 is just 1. So I'm left with negative 5. Now that negative can go anywhere. It doesn't have to go in the denominator. And when I go ahead and simplify this, 1 plus negative 3 is negative 2. So I do get that the solution works. And I know that this is a true solution of the problem, not an extraneous one. So I would type this in for my answer. All right, let's do one more example in this video, and then we'll do a little bit more. So here I have my denominators, but this one they're a bit more complicated. So when they're written like this and you have addition or subtraction in your denominator, you want to keep that factor together. So when I write my factorization, it's going to be x minus 3 as a group, not just x and not just negative 3. So that's a little bit different when you have a complicated denominator. Now, let's see if I can get this to work. Okay. Here I have the same denominator again. I don't need to repeat it twice. So if I only have it once and there's no squares or anything like that, then I don't need to write it again. Side note, so if you had something like this, where you had a square there, then yes, then you would need to have a square here too, because you would need 2 of them. So you do have to match each denominator, okay? So in this case, your LCD would be x minus 3 squared. But I don't have that here, I just need it once. If I don't have a denominator, don't worry about it. That's going to be my LCD. So I'm going to multiply everything through. By my LCD. Even the 9, so don't forget that 9 there. And then I'm going to start canceling. Now when I cancel, I have to cancel this as a group. So you can't just cancel the x or just cancel the 3. The whole thing has to be exactly the same. Same thing here. Whole thing is exactly the same. So when I'm left over, in the first part, I just have an x left. And then here, I just have a 3 left, right? Technically, you have a factor of 1, but we don't need to multiply through by 1. Now here, a little bit of work. I can distribute that 9 throughout. So I have 9x minus 27. I'm going to keep solving. So I do have like terms here. So I'm bringing the 9x down, and then I have minus 24. I'm going to bring my 9x to the left so I can separate out my different kinds of terms. And then I'm going to go ahead and divide both sides by negative 8. And I get x equals 3. Now remember, you need to watch your denominator, right? Denominator cannot be 0. So if I look at my denominator here, I need to make sure that x minus 3 is not equal to 0, because that would be my denominator. Well, when I go to solve this, and even though it's a not equal sign, it solves the same way. I see that my answer cannot be 3. But that's what I got. So this is bad, right? I'm not supposed to get 3. 3 is bad. 3 would make my denominator 0, which is undefined. So this is not a real solution. This is an extraneous solution in this case. Okay. So there is no solution here. There's no other answer. I only had one answer. I had to throw it out. It doesn't work. When I plug it in, it makes that denominator 0, and that is a problem. So it is gone. So one way to write no solution, you can also write it using this symbol here. That's the symbol for the null set, meaning that there is no solution. So you'll see in your text and in the homework, they use this symbol a lot for no solution instead of writing out the words.